Okay, welcome back. Last time we were discussing the stereochemistry of addition of a nucleophile to a carbonyl in an acyclic system first, which is attached with an alpha stereogenic center, and we have covered the Cram's rule, the different kinds of rules like Cram's rule, then Felkin's rule to predict the major product that is formed. We also have gone through the Prelog's rule, and that is a remote induction kind of thing, but that was very helpful in identifying the configuration of an alcohol where the stereochemistry is not known at the alcoholic center. Now, then we went on to the cyclohexanone system, and we gave one more model in cyclohexanone, that is the Cyclic model. So, if we take tertiary butyl cyclohexanone, then what happens if we treat with sodium borohydride, then there is the major product formed is the axial alcohol, is the equatorial alcohol and not the axial alcohol. Remember, the equatorial alcohol is formed by the axial approach of the borohydride. So, the borohydride approaches from the axial phase to give the equatorial alcohol. Okay. And to get the axial alcohol, the borohydride approaches from the apparently more sterically accessible equatorial side. So, here this hydrogen comes from the borohydride. So, that is approaching from the equatorial phase. So, there was lot of problems in explaining this reaction, the stereoselectivity of this reaction, and finally, what happened, because there are the steric factors which is bothering people, that these hydrogens should offer steric hindrance to the approach of the borohydride, and this reaction is called steric approach control, because it is not product stability controlled. As I told you, this is an exothermic reaction. So, you have to consider both the reactant and the substrate at the same time. Okay. So, that gives you this, that you have to involve the borohydride as well as the carbonyl. So, when borohydride approaches, there is this the steric hindrance expected from the hydrides. Now, later on Felkin gave a very good model, which is based on the stereoelectronic effect, the stabilization of the transition state. See, when the nucleophile approaches from this side, so then if there is the antibond, if you consider the antibonding of this interaction, the carbonyl goes like this. So, this orbital will now interact with the nucleophile orbital, and that will give two scenarios. One is bonding, another is antibonding. Sorry, when there is bonding, then the nucleophile orbital will, this is the bonding scenario, and in the antibonding scenario, because they are in opposite phase. So, what will happen, that the nucleophile will have the orbital towards the back, and this orbital also will not try to face each other, they will be posing, and there will be a small lobe on the front side. Okay. So, this is the antibonding scenario, and in the antibonding scenario what happens? In the antibonding scenario what happens now? I put the tertiary butyl because you want to stop the flipping, that is the locking group. In the antibonding scenario, these hydrogens are almost aligned to this antibonding, empty antibonding orbital of the carbon nucleophile bond, and that undergoes hyperconjugative stabilization from electron donation from the hydrogens, axial hydrogens at C2 and C6. Okay. At C2 and C6. In this case, if you draw that is from the approach from the axial phase. If it approaches from the equatorial phase, then the diagram will be that the antibonding lobe will be bigger on this side, the nucleophile is here. So, nucleophile lobe is like this, antibonding, and this is the oxygen. This is the oxygen lobe. Okay. So, now what is happening, that the only orbital that can donate here is these carbon-carbon bonds. Okay. These carbon-carbon bonds, and that is much poorer electron donor than the CC bond is much poor electron donor than CH bond. So, ultimately the major product is the approach from the axial phase leading to the equatorial alcohol. So, that was the status at that time. Then people started arguing that this may not be an ideal system to test Cyclic's hypothesis. Cyclic what is said, that the transition state is stabilized due to electron donation from adjacent bonds to the antibonding to the incipient, that means the forming antibonding orbital. So, now what was the criticism? The criticism was that because the cyclohexane, the two faces are not identical, Okay. This equatorial phase is geometrically not same as the axial phase, because in the axial phase you have these axial hydrogens, but in equatorial phase you do not have those. So, they are not offering the same type of phases to the approach of the hydride. So, that may not be an ideal system to really convince that ourselves that the Cyclic model is correct. So, in that case what we need to do is to take a carbonyl system where both the sides are facially symmetrical, both the faces are facially identical. Okay. Like if you take a bicyclic system like this, this is by the way called a Norbornene system. A Norbornene system, and if you put a carbonyl here. Okay. Now, what happens? Now, this is perfectly symmetrical. So, if the nucleophile comes from this side or this side for a carbonyl addition, you get the same product, because you do not have any other substituent in the system. But what happens here, this phase is geometrically same as the other phase. Okay. So, in that case you cannot say that there is kind of steric differences in the approach of the nucleophile to the carbonyl. Okay. Now, what you do, you put some substituents here. Suppose I put a substituent R and R. Okay. Now, what happens, the faces geometry are same, because these R groups are not interfering with the faces, because they are pointing downwards. So, if the faces are identical, now the question is, now what happens, first of all, if you do a sodium borohydride reduction, suppose, or a methyl lithium addition, Okay. So, what are the products? If sodium borohydride, you get so you get either this OH and H, that means the H is approaching, the borohydride is approaching from this face. So, that is path A. So, if the borohydride is approaches from the path B, that means from this side borohydride, then what happens? Then you get the, okay, this R1 has to be, R has to be there, otherwise these products will become identical. So, now you have OH on this side and H on that side, R will be here and R will be there. So, these are the products. Make sure that what I am saying, that is right. So, this is the path B. For methyl lithium it is the same. So, I just exclude the methyl lithium. If the methyl comes from this side, so you get OH on that side. If the methyl comes from that side, the OH on the left side, it is similar. So, argument will be same. The question now is which one is the major product. Now, this is a work done by Professor Govardhan Mehta, the famous organic chemist in India. So, he wanted to, he was a firm believer of Cyclic model, and then, but because Cyclic had lot of criticisms because of the two unequal faces of cyclohexane. So, he studied this Nor-Bornean system, Nor-Borneanone, and where the two faces are identical. Now, what happens that what is the major product? That was the key issue. So, what he found that the product ratio depends on the nature of R, on the nature of R groups. Okay. R groups can be two types, either electron donating or electron withdrawing. Okay. So, that is the first thing, that it depends on the nature of R. So, how does it depend? Now, let us draw the orbital picture like what Cyclic did, that when the nucleophile, in this case borohydride, okay, approaches from this side, the antibonding orbital will be, so that will be elongated now, that will be broken little bit. Okay. So, the antibonding orbital of this carbon nucleophile bond will be have a bigger lobe on this side and a smaller lobe on this side, and this is empty. This is the antibonding scenario. Okay. Now, if you look at this geometry, this line of the axis of this orbital, that is not exactly parallel, but they are not also orthogonal. Their angle is not that much. So, there is a possibility that these bonds, this is actually the middle of these two bonds, is in the middle between the two bonds. So, that those two carbon-carbon bonds now can donate to this orbital. Okay. On the other hand, if it is on the, if the attack takes place from the other side, so then what happens? You have so that is the nucleophile. So there will be a small orbital and there will be a bigger orbital. Now these are the bonds. Now these are the bonds which are going to interact with this empty orbital. So these are the bonds which are going to interact with this orbital. Earlier, these are the bonds which are going to interact with this. Okay. So question is which interaction? We know carbon-carbon donation is much less, but that is in comparison to the carbon-hydrogen. So if it is a carbon, different types of carbon-carbon, then we can make a comparison. Okay. Remember, there is R here and there is R here. Now, if R is electron withdrawing, then this will be a poorer donor. This CC bond will be poorer donor. Okay, because it is electron withdrawing. So, it will not allow the carbon-carbon electrons to interact with the empty antibonding orbital. On the other hand, if R is, so that means in that case we can expect, that means in that case this is a better donor than this one. This one is a better donor than this one. So, in that case this will lead to the major product. Provided R is electron withdrawing, that is the important point. If R is electron donating now, so if R is electron donating now, so let me change it to electron donating, exactly opposite situation will happen. Now, what will happen if R is electron donating? Then this will be a better donor, because there will be more electrons pumping into this carbon-carbon bond, say by inductive effect. Suppose these are methyl, suppose alkyl groups, then that will happen, and then this will be a better electron donor. So, if it is a better electron donor, now this will happen, this stabilization will be more with respect to this stabilization. So, in that case this will be the major product. Okay. So, this is a very nice example of the validity of the Cyclic model when the nucleophile attacks to the carbonyl. Okay. So, we are not going into other examples because this is a, as I said, this is a foundation course, but up to this point is okay. I think for you guys it will be easier to understand up to this point. Okay. So, if a problem is given on nor Born unknown, you can easily explain from which side the nucleophile will come. That depends on the remote effect of these R groups. This is remote, see the attack is taking place here and these R groups are quite far away. Okay. Now, the same thing I did not mention, the similar thing happens in Cyclic model, that cyclohexanone also. See, in cyclohexanone we know that the equatorial alcohol is obtained in a predominant amount. Now, that whatever be the ratio of the axial and equatorial alcohol, axial is to equatorial. We know that the equatorial is predominant, that is true, but that ratio can be perturbed if you put remote substituents. Like here, if I put substituents, so not here. So, if I put substituents here, suppose cyanide, if I put cyanide, then this carbon-carbon bond, because of the electron withdrawing group of cyanide, that becomes even poorer donor to that antibonding orbital. So, in that case the axial alcohol will be even less, axial alcohol proportion goes down. I hope this is clear, because now if you look at the transition state. So, now for the axial alcohol the nucleophile has to come from this side. So, you have a bigger orbital on this side, that is the antibonding orbital, and now because of the presence of the cyanide, this is much worse than a simple carbon-carbon bond. On the other hand, if cyanide is replaced by methyl, then the proportion of the axial alcohol, axial alcohol proportion goes down for cyanide. Axial alcohol proportion goes up for R equal to methyl, but do not expect that this will be the major product. What I am saying that always the equatorial alcohol is the major, but the percentage of axial alcohol is perturbed while going from cyanide to methyl. I think that is also an added proof that Cyclic model is valid, because this type of other models like Felkin's model, which actually relied on the eclipsing interaction with the C2C6 hydrogens, that cannot explain this remote functionalization effect. Okay. So, that is more or less all about this cyclohexanone, the reduction at the carbonyl, that is a big chapter. Okay. In the first we did the acyclic system, then we come to the cyclic system. One more point I always want to mention here, that if the nucleophile happens to be really very big, or if you have, suppose you have a methyl here and a hydrogen. So, you have axial methyl, and if your nucleophile happens to be very big, then the approach, whatever stability we are talking about of the antibonding orbital, all will be washed out by the steric effect. The steric effect now takes the control. The steric effect of the approach is too much now because of the methyl and the hydrogen, and the nucleophile is also very big. So, in those cases what happens? It is always the axial isomer, axial alcohol predominates. So, keep that in mind. Okay. For simple nucleophiles like borohydride, or for simple alkyl lithiums like methyl lithium, the smallest alkyl lithium, the whatever I said, that the Cyclic model, that the predominant formation of the equatorial alcohol stays. But if there is too much steric conjugation, either due to size of nucleophile or due to already present axial bulky axial groups, then the equatorial approach is favored and the equatorial approach is favored, and the product will be axial alcohol mainly. Okay. One more point, I think when I told you about this, so steric effect, so there is a continuous contradiction between the steric effect and the stereoelectronic effect. Okay. So, sometimes steric effect wins, sometimes stereoelectronic effect wins. So, that is evident from these examples. Now, remember when we asked for the, when we read the rate of oxidation of these two, chromic acid oxidation of these two alcohols, our result was that the axial alcohol was oxidized at a faster rate, and the reason is that the mechanism is such that the first it forms the chromate ester, but which is a very rapid process, and this is not the rate determining step. The rate determining step is the breakage of the chromate ester. Okay. And the breakage of the chromate ester releases the steric strain that is associated with the chromate ester and these axial hydrogens. So, decomposition of the chromate ester is the rate determining step, and that is why axial chromate esters undergo faster breakage, and that is why ultimately the axial alcohol reacts faster. Interestingly, just exactly the opposite effect is there if you have a ester here CO2Me and an ester here CO2Me. So, an equatorial ester versus an axial ester. In this case, what happens if you do, I think this was covered maybe, the saponification, what happens, the saponification rate, it is just a recapitulation. In this case, this reacts faster, because it is the rate determining step which will decide. In the rate determining step, the base attacks and the steric crowding increases, and if the steric crowding increases in the base rate determining step, then the reaction becomes slower. So, that we find a rule of thumb, if the steric crowding increases in the rate determining step, then the rate becomes slower. So, that molecule will react in a slow fashion. If the steric crowding decreases during the rate determining step, then that molecule will react faster, and that is what is called steric acceleration. The first one is steric retardation. Okay. Now, let us go through some of the modern developments of asymmetric synthesis. Okay. Some modern developments of asymmetric synthesis, and I have told you that in asymmetric synthesis, what you need to do is, there are several ways to do asymmetric synthesis. One is that your starting material, wherever you are doing the reaction, suppose here this carbon, but you have a built-in asymmetric center somewhere, and that then induces the asymmetry of the, controls the asymmetry of the, that is generated at the neighboring carbon. Okay. And that we have seen, that where the Cram's rule have been applied, the Prelog's rule have been applied, those molecules already had a stereogenic center, built-in stereogenic center. Okay. So, this is, that means you start from a chiral molecule, and then you start generating chiral center at different positions. Okay. And this is an approach, this type of asymmetric synthesis, because you are getting only one isomer over the other in major amount. So, this type of approach is called chiron approach. That means, you started with a chiral molecule and then you generate the other carbon and control the configuration. That is called the chiron approach. Okay. Then you have, now there are different chiral materials available in our day to day life from natural products. I told you the natural products are always chiral, and some of the natural products are very good chirons, like sugars, like amino acids, okay, because they have built in chiral centers. Then comes the chiral auxiliary approach. Chiral auxiliary approach. What is that? Chiral auxiliary approach is that you have a symmetric molecule. So, there is no chiral center present in it, symmetric molecule. Now, if you do the reaction in a symmetric molecule and if the reactant is also achiral reagent, then what happens? If you are generating a new chiral center, then the transition state for formation of the new chiral center will be enantiomeric, because you do not have any built in chirality involved earlier. So, here you will not get any asymmetric synthesis. So, no asymmetric synthesis, no asymmetric synthesis. That means, you will not get any discrimination between the R and S that is produced. So, in those cases what happens? What you do, you attach a, in the symmetric molecule you attach a chiral material, a chiral entity, okay, a chiral entity through a covalent bond, and then do the reaction. So, now what you have, earlier it was a chiral starting material, but once you put a chiral entity L, so whole thing becomes chiral. The whole thing becomes chiral. So, now if you do a reaction, so you are doing a reaction on a chiral material. So, if you, and a particular chirality, this has got a particular chirality. So, suppose this is generating a chiral center which has got R or S configuration, and your starting chiral entity has a R configuration. So, your transition states will be diastereomeric, because you are producing now diastereomers RR and RS. So, if these are diastereomers, so that means you are going through a diastereomeric transition state. So, there is a possibility that you can get enantiomeric excess, diastereomeric transition state. So, now if there is a sufficient energy gap between the transition states, so you will get one over the other in large excess. Okay. So, this is called chiral auxiliary method. So, you put this chiral entity, attach it by a covalent bond to your achiral substrates, and then after the reaction you take it off, chop it off. So, what you end up is, so if you take this off, this R portion which comes from the L, so you are left with R and S. So, if one of them is measured, so you get either R or you get either S. Okay. So, this is called the chiral auxiliary method. Now, let us see here. Chiral auxiliary, what it says, a chiral control element temporarily incorporated into the structure of the substrate in order to direct the stereochemistry at new stereogenic centers formed in a reaction. The auxiliary is removed either immediately during workup or in a separate subsequent step and may be recovered for reuse. Okay. So, definition is very clear. I have an achiral system, I put a chiral entity, that is the auxiliary, do the reaction, this auxiliary now induces the asymmetry when it is generated, and after the reaction you take off the chiral auxiliary. That can be taken, some reactions the chiral auxiliary falls apart during the workup, in some reactions it has to be taken separately. Some of there are plenty of chiral auxiliaries available nowadays. They are made from the amino acids, mostly from the amino acids or other natural compounds, like this is obtained from menthol. You can see 8-phenyl menthol is a chiral auxiliary for Diels-Alder chemistry. Diels-Alder reaction is a 4+2 cycloaddition. Then alkylation of enolates, enolate alkylation, that means you are putting an alkyl group alpha to an ester or a carbonyl with a stereo control, then also this type of chiral auxiliary can be used. This is called, according to the names, the auxiliary scientist name who has discovered. So, they have named the chiral auxiliary, like this is called Evans chiral auxiliary, this is called Myers, this is 8-phenyl menthol, I think this is maybe Corey's chiral auxiliary. Now, what happens, suppose I want to alkylate an ester. Suppose I want to alkylate an ester group, say I have CH3, CH2, COET. Now, in alkylation, what you need to do, you convert it to an enolate. So, you have to add a base, but these bases are like say alkyl lithium reagents, and then what happens, it goes into the, so these are usually organometallic reagents, say alkyl lithium, butyl lithium suppose. So, this will be the metal, so this will be OET, and then depending on the substrate, now you have this. See, there are two types of enolates that can be formed. Suppose I get this enolate in predominant amount, suppose I get this one, okay. It also depends on the condition, reaction condition, which enolate will be formed. Suppose I get this enolate and then I do the reaction with the alkyl halide. So, this comes back and now this comes and attacks the R, the X goes out. Now, since I do not have any chirality involved in this system, this is not chiral and the whole system is flat. So, what happens, the R can come from the Rx can come from the top side or Rx can come from the bottom side, like your ray phase. So, you can work out which is ray phase, which is Psi phase. Okay. So, this is your, this is 1, that is 2, that is 3, that means this is the ray Psi phase and the back side is the ray phase. So, anyway, the percentage of because these two transition states are enantiomeric, or the other way around, since these two phases are enantiotopic phases, how do you know they are enantiotopic phases? Because the ultimate product is enantiomer. So, they are enantiotopic phases. So, ultimately you will get both the products, both these are from the ray side. So, R will be delivered from both ray and Psi phase in a 50-50 manner, in a 1:1 manner. So, you get a racemic compound. Okay. So, now in order to introduce asymmetry in this reaction, so what you need to do? So, you need to attach, see, instead of OET, you see OET, O-ethyl, we attached that what I showed, the Evans chiral auxiliary. You do not need to know what is, how do you attach, but it is there in the slide that how do you attach this chirality. So, this auxiliary. So, you have this auxiliary, put butyl lithium. So, this becomes N minus, then you put your that alkyl chloride, acyl chloride instead of OET. OET is chlorine is a better reactive system, acyl chloride. So, you get the similar system CH3, CH2, CO, and then the auxiliary, that Evans auxiliary. Okay. Then what you do? You do the LDA minus. LDA is another base, it is called lithium diisopropyl amide, and that forms the anion here, and the anion then goes to the conjugation with the carbonyl. So, you get the enolate, and once the enolate, then you add your alkyl halide and then do the alkylation. That is the whole thing is shown in this slide. Okay. So, this is the compound. So, usually what happens, this type of enolate is obtained, that means the methyl is on this side and the hydrogen is on this side, and this is the OLI, this is the carbonyl. There is a chelation formed between this OLI and the carbonyl. So, that will be directed towards that direction. Okay. Remember, this carbon nitrogen bond can rotate, this carbon nitrogen bond is in a position of rotate, but that rotation is restricted because of the formation of this chelate. So, once that is restricted, now this is the isopropyl group that is pointing downwards, that came from the chiral auxiliary. So, that is decided by the chiral auxiliary, and the chiral auxiliary that was taken, this isopropyl group is alpha. Okay. Now, what happens, this big group will stop the ethyl iodide, that is the alkylating agent, to come from the back side. So, it is the front side from which the ethyl iodide will approach. Okay. So, if the ethyl iodide approaches from the front side, so this is the other way to see the enolate. So, the ethyl will be so that is on the top side. So, that is this ethyl, and this methyl is still alpha and the hydrogen is beta. So, the most important thing is ethyl comes from the top side, and that is the product, predominant product that you will get. So, this is the R compound. Okay. If you take the other chiral auxiliary, the beauty of Evans chiral auxiliary is that if you take the other chiral auxiliary where the isopropyl is beta and the hydrogen is alpha, then you get exactly the opposite compound, the S compound. So, this is then there are ways to take this off, like the earlier slide. After the alkylation is done, then what you do? Then you hydrolyze this hydrolyze, this is an amide, this is not an amide, this is a urea type of linkage, NCO-CO. So, you can hydrolyze with lithium hydroxide, hydrogen peroxide. That was all done by David Evans at Harvard University. So, he hydrolyzed it, and one can get these carboxylic acids in 98%, more than 98% enantiomeric excess. See, at this point you have to say 98% diastereomeric excess, because at this point the chiral auxiliary is S. If you calculate if you determine the configuration here, this was 1 nitrogen, this was the 2 and this is the 3. So, apparently it looks like R, but actually the hydrogen is beta. So, this is S and this is R. So, now you have the formation of RS and SS. So, these are diastereomers. Out of these, RS is greater than 98%. So, that is why here you have to write 98% diastereomeric excess, and once you hydrolyze, then you have the enantiomeric excess, because now you are handling only enantiomers. So, this is the Evans chiral auxiliary method. I will just quickly give you the essence, the modern what is the status. Evans chemistry is very well used, not even alkylation chemistry, it was used in aldol chemistry also. Very similar kind of auxiliary is used in aldol chemistry. There is a third approach, see chiron approach, then auxiliary approach, and there is a third approach, that is the chiral catalyst. So, what happens here, your substrate, the achiral substrate forms a complex with the catalyst, but the catalyst is chiral, and then the reaction takes place and the catalyst goes away, and what you get is your reaction is such that it creates a chiral center and maybe multiple chiral centers in one reaction. That is also possible, that is even better. See, that is also, again I point out that in a particular reaction, if you can generate one is okay, but if you can generate more than one in one reaction, then that reaction will be more acclaimed in the literature. Okay. In fact, this asymmetric synthesis about few years ago, maybe 10-14 years back, three people shared the Nobel Prize for asymmetric synthesis. And why this is important, I told you that many of the drugs are chiral drugs, and to make those drugs in one enantiomeric form is extremely important. I told you about the thalidomide tragedy, and after that people have devoted lot of time in achieving asymmetric synthesis, and it was Barry, Sharpless, and then Noyori, and there was a third person, Noyori, Sharpless, and some other person, now I am forgetting. These three shared the Nobel Prize for asymmetric synthesis. Okay. So, we are just discussing their strategy was, unfortunately, the chiral auxiliary based strategy was not recognized by the Nobel Committee, because what happens, you have to attach the auxiliary in a 1:1 stoichiometric manner. Okay. 1:1 stoichiometric manner. But if you have a catalyst, if you do the reaction, the catalyst attaches to the substrate, do the reaction, get the chiral compound out, the catalyst goes out, and this catalyst then catalyze fresh substrate molecules. Okay. So, this is basically the lesson was learned from nature. This is how the enzymes catalyze reactions. Enzyme takes a substrate, does the reaction, and when it does the reaction, it is always stereoselective, and it is asymmetric. The reaction is asymmetric, and then this goes out, the enzyme is free, another molecule comes, and then the reaction takes place. So, in this way, one enzyme molecule can convert several substrate molecules per second, and that is a term which is called turnover number, that one molecule of the catalyst is turning how many substrates into products per minute, okay, or per unit of time, whatever is the unit of time. So, this has got an advantage, and another, that means you can use much less catalyst, much below the stoichiometric amount. And today, even 1 mole % or below 1 mole % catalyst has been used to generate to achieve asymmetric synthesis. So, what is Sharpless epoxidation? That is the Nobel Prize winning work. You know that double bonds can be epoxidized, okay, and the epoxidation can, again, the epoxidation is a phase dependent phenomenon, that when you form the epoxide, either the epoxide can be formed from the top side or from the bottom side. Okay. Now, there are reagents to do. So, usually you get plus minus mixture, 50-50 plus minus mixture of the epoxide. So, when you do the reaction epoxidation, suppose with MCPBA, metachloroperbenzoic acid, or there is another reagent which is called titanium isopropoxide alkyl hydroperoxide, like T-butyl hydroperoxide, then these double bonds are epoxized. One difference between T-butyl hydroperoxide and titanium isopropoxide combination is that it only epoxidizes compounds which are allylic alcohols. So, there must be a wedge here, and then CH2, then a double bond. Okay. Now, Sharpless saw this reagent, that this reagent is able to epoxidize the double bond. So, what he did, see, if you, again I repeat, if you take this compound and do the epoxidation with either of these reagents, so what you get, the beta epoxide and the alpha epoxide in equal amount. Okay. But if you take, like this experiment, see, if you do not have any chiral reagent, you will, this is T-butyl hydroperoxide, you will get 50-50 mixture of this. But what Sharpless did, that titanium isopropoxide has 4 ligands, 4 isopropyl ligands. So, he added this diethyl tartrate, which can displace 2 of the ligands in titanium. So, form a titanium will be complexed now with the isopropoxide as well as with the diethyl tartrate. Okay. And then when this attaches to the titanium complex, now it is attaching to a chiral titanium complex. So, epoxidation now can be diastereoselective at this stage when it is bound to the catalyst. Then the catalyst goes out and you see which epoxide you are getting. Now, what Sharpless observed, that if you add minus diethyl tartrate and titanium epoxide and the titanium isopropoxide and T-butyl hydroperoxide all together and the allylic alcohol, so you get discrimination, you get either the alpha or the beta epoxide. Now, which one you get? There is a mnemonic device, mnemonic way to remember that if you use minus, this is minus diethyl tartrate, if you use minus diethyl tartarate, then the epoxy, and if you write the alcohol in this way, that means the OH is towards your right and the bigger alkyl group is towards the left of this carbon, of this carbon, then the vinylic carbon, then what happens, the epoxidation takes place from the top face, provided you write this in this fashion and provided it is minus diethyl tartarate that you are using as the chiral ligand, okay, for the titanium. If you use the plus diethyl tartarate, you get the epoxidation from the bottom face. One example is this. See, this is the cinnamyl alcohol. Now, cinnamyl alcohol, if you just it is actually written in the way that was shown in the mnemonic device, that basically if you turn it a little, then the phenyl will be on this side, then the double bond and then this CH2H. So, in this case if you are using plus, now this they have used plus diethyl tartarate. So, if you use plus diethyl tartarate, what was the earlier result? If you use plus diethyl tartarate, then it is the bottom phase. Let us see, minus diethyl tartarate. They used 6 mole % plus diethyl tartarate, and here they used 6 mole % of this is minus. I think there is something wrong here. This should be minus diethyl tartarate, because the minus diethyl tartarate gives from the top face. So, this is minus diethyl tartarate and this should not be plus, minus diethyl tartarate. So, that gives the beta compound and this should be plus diethyl tartarate, not the minus. So, if it is plus diethyl tartarate, then it will be the alpha epoxide, okay, according to the mnemonic device. See, you have written it in the double bond wedge this fashion, okay, and these are actually written like that, only slightly inclined, okay. Just remember that you have to write this in this fashion. If it is minus, then it comes from the bottom in the top face, that is beta epoxide. If it is minus diethyl tartarate, plus diethyl tartarate, then it gives the alpha epoxide. So, just to finish up, so what is Sharpless method? That you write this compound in this is your R group, this is the hydrogen, and your reagents are, if you use reagents are this T-butyl hydroperoxide, that is the oxidizing agent. Then you have the catalyst titanium isopropoxide, I just write OR4, and you have the diethyl tartarate, Now, you have this diethyl tartarate can exist in plus and minus forms, that is optically active forms of tartaric acid. So, if you use minus diethyl tartarate, then it will be the epoxide will come from the beta phase, okay. So, that is the, and if it is plus diethyl tartarate, I just want to make clear, because there was something wrong in that slide, TBHP, T-butyl hydroperoxide, and you have titanium isopropoxide. I just wrote OR4. Then what you get, the epoxide comes from the bottom phase. So, you have this, and this is the epoxide. Okay, this is the hydrogen. This is beautiful in the sense that you get very high enantiomer selectivity, and the other thing, if you have noticed, that it creates two stereogenic centers at the same time. So, two stereogenic centers with a high degree of asymmetry, Okay. So, that is the, so I give you some glimpse of the modern asymmetric synthesis. I just explained you the Evans chemistry, and I just told you about the Sharpless chemistry. I did not go into the mechanism how the oxygen is delivered from the beta side when minus diethyl tartarate, that is too complicated for you at this stage, but as you grow older and attain higher stereochemistry level courses, I think I am sure that will be done, because there are other, I said Nouri also got the Nobel Prize by doing the asymmetric hydrogenation, and that was also I just excluded from this part. That is the part of the asymmetric synthesis in detail is usually a part of the advanced stereochemistry courses. Okay. So, we stop at this stage regarding the asymmetric synthesis, and next day we will try to that is the last class, and that will we will again recapitulate some of the concepts, and if something is left behind we will also cover that in the last class. Thank you.